Okay, so let's start today's lecture. Okay, so we're going to continue with second order equations, but now we are we'll talk about some applications of second order equations. So very typical type of application problem that we will be talking about is called mechanical vibrations. Okay, so sorry. So this, let me use the right ink. Okay, so we're going to talk about mechanical vibrations. Okay, so the mechanical vibrations is a very typical type of application problems for two-dimensional, so second order equations. Okay, so and it is very important to pay attention to application type problems during this course. Okay, for example, let me, as I can remind you, we talked about first order equation like tank problem, right? So like the population model, okay, Newton's law of cooling. These are just applications. So they're going to be occupy a very important portion of your exams of this course regarding the applications of differential equation. So mechanical vibration will be a very important type of application of second order equations. Okay, so in order to consider mechanical vibration, let me first draw a picture. Okay, so by mechanical vibration, it usually type of problem is about a ceiling, and there is going to be a spring attached to the ceiling, and then there is a mass attached to the spring. Is that good for everybody? Okay, so let me say that the original spring has a length capital L. Okay, so the original spring has a length capital L. Okay, so let me draw the picture like this. Okay, so for example, I will say that the original length of the spring is capital L. Is it good for everybody? Okay, so now if the natural length, so the natural length, okay, so natural length of the spring is equal to capital L. Suppose the natural length of the spring is equal to capital L. Then if you attach a certain mass to the other end of the spring, while the original end of the spring is attached to the ceiling, then there is being an elongation, right? Because of gravity. Because of gravity, there's going to be an elongation of the spring, right? So the spring is going to be elongated by a certain distance. So let's say it will be something like this. Compared to the original length, it is going to be elongated by small l, right? So the small l is the elongation. Initially elongation is a small l. Is a good for everybody, right? So that's going to be your scenario, and then you're going to reach a certain equilibrium, right? So that means that if you just if your mass is just elongates the spring by small l, then it reaches, okay, so system reaches equilibrium. Okay, so the system reaches equilibrium, so that means m multiplied by g is equal to L multiplied by K. Is that good for everybody, right? So some people ask me, what's K? K is what we call it Hooke's constant. Is that good for everybody, right? So K is the so-called Hooke's constant. By our course in mechanics, the Hooke's constant is just providing you the resistance force, right? So it provides you the resistance force. By resistance force, it means that whenever the spring is deformed, a resistance is going to be formed in the spring, and the resistance is always to the opposite direction of the deformation of the spring. So that means if the spring is elongated, it's going to drag you back. If the spring is like compressed, right? So then it's going to push outward, right? So resistance force is always to the opposite direction of deformation, And the amount of resistance force, the magnitude of the resistance force is always the proportional to your deformation. And the proportionality constant is what we define by Hooke's constant, right? So this is the so-called Hooke's law of springs, right? Springs. So this is sometimes also called spring mass system. Okay, so it's sometimes also called a spring mass system. Good for everybody. Okay, so that's always called spring mass system. Okay, so that's kind of the issue. Okay, so about the original vibration system. So how does the vibration comes up, right? So how does the vibration come up? So here we're going to consider the following problem: that the motion of a mass m hanging on the end of a vertical spring of the original length small l. Okay, so here maybe I will use small l. Okay, so that's just to make myself agree with the lecture notes. Okay, so I will say that I mean it's completely fine to switch. Okay, so I will say the original length is small l, the elongation is capital L. Okay, so that's mg is k capital L. Okay, so I'm just going to do it in this way. Okay, so but it's okay. I mean, originally it was small l and capital L. You switch, but it doesn't matter. It's just a symbolic issue. Okay, so but let's agree with the lecture notes. Okay, so here it says that the elongation is capital L. However, here we are going to describe the motion, right? So I want you to describe the motion. So what does it mean describing the motion? Well, describing the motion, it means that you want to describe the position of the mass. So first of all, how does the motion come up, right? So how does the motion come up? Well, if you want to have a motion, then the situation is more or less like this. So let me say this is the equilibrium position, okay? So is the equilibrium position the original length of the spring? Well, it's not, right? Because the spring has to have length small l, right? So the original length, it was small l, okay? So that means small l plus the elongation, capital L. That will be the length for the spring at the equilibrium position. Because this capital L, you must have mg is equal to k capital L. Capital L has to offset the gravity, gravitational force. Now, how does the vibration comes up, right? So how does the vibration come up? How do we create a vibration? Well, you're going to create a vibration by, let's say, dragging. Okay, so you want to drag the m, like the, let's say, to the downward direction a little bit more. Okay, so let me say, for example, you drag the another distance, right? So let's say of u, right? So that's a dragging. Okay, so you drag this mass to downwards a little bit. Then it means that the spring is kind of too much elongated because it's not the equilibrium position. So that means there is going to be a much more, I mean, there is going to be additional resistance force dragging the mass upwards. Is that good, family? So if you just release, okay, so if you just release the mass at this position, not at the equilibrium. So this is the equilibrium, right? So this is the equilibrium. You just release the mass at the position that's kind of deviates away from the equilibrium. Then this resistance, this additional resistance force is going to lead to a certain oscillation of this mass. Is that good, family? It's going to come up, and then it's going to be pushed down, and then come up and push down. So that's what we usually see in, we observe such phenomenon very commonly. Is that good, family? Okay, so, and vice versa, if you have this picture, okay, so if you have the following picture, that means, for example, your original length is L plus L, that's equilibrium, but then you're going to push upward, right? So you're going to push the mass upward to a certain distance. So that means you're going to push the mass upward to a certain distance. Then if you release the mass, it is going to come down first. And after coming down, it will start come up and then start to oscillate again. Is that good, family? Okay, so our goal is to describe this oscillation. Is that good, family? That's why we sometimes call it vibration, and the same thing as oscillation. Okay, so it's same thing as oscillation. And so we're going to want to describe such a vibration or oscillation phenomena. Is that good for everybody? Okay, so that's kind of the target for this lecture. Okay, so how are we going to do that? Well, you have to if you want to do that, then you have to understand how to describe first of all the position of the mass. Is that good for everybody? Right? So how to describe the position of the mass? Well, some people are going to say, well, the position of the mass is vertical, so I can describe it by the length of the spring. But that's not a very good idea, okay? So what we are going to do is that, so the position, so this is very important. So I have to use black ink, okay? So this is going to be very important, okay? So this is going to be very important, is that the position, okay? So position of the mass is measured, okay? So is measured with respect, okay, so with respect to the equilibrium position, okay, so equilibrium. Equilibrium position. So that means we're going to measure the position of the mass with respect to the equilibrium position. So equilibrium position is 0. Is that good for everybody? So what's equilibrium? This is the equilibrium position where the elongation of the original spring is or has already occurred. It's already elongated, but the mass is subject to 0 force because the spring force KL multiplied by L just agrees with mg, so that you're going to have this identity. So this is what we call it the equilibrium position. So the equilibrium position is always denoted as your 0. Okay, so it doesn't mean that the original length of the spring is denoted by 0, but the equilibrium position is denoted by 0. Is that good for everybody? Okay, so this is very, very important. First, very, very important fact is that you must measure the position of the mass with respect to the equilibrium position, which means that the whole system is steady, and in that case, there is already an elongation of the original spring. Is that good for everybody? Okay, so the position. Now, the second thing is that in our measurement, there's going to be a sign issue. Okay, so for example, here, if you elongate, so you go downwards, right? So the downward direction is always going to be positive. Okay, so the downward, okay, so downward direction, okay, so is positive. Okay, so the downward direction is going to be positive. So what does it mean? It means that if the elongation is already initially it was downwards, then it's going to be measured as positive. Okay, so otherwise, okay, so that means if the initial elongation is downwards, then it's going to be measured as positive u. If it is upwards, then it's going to be measured as negative u. So the downward direction is positive. So this is the positive direction, and this is the positive direction. So if you have both of these agreements, okay, so you have both of these agreements, then you can describe, okay, so the third fact is that we're going to describe, okay, so the position, okay, so the position of the mass, okay, so the position of the mass by relative displacement, right? So relative displacement with respect to equilibrium position. Okay, so we're going to describe the position of the mass by the relative, okay, so it's the relative displacement with respect to the equilibrium. So what does it mean? It means, for example, if you elongate, right, if you elongate the spring, the relative displacement means that the relative position with respect to the equilibrium. Equilibrium is already the 0 position is already the equilibrium position. So with respect to the equilibrium, let's say if you elongate your spring by u, then the relative displacement is just u. If you kind of compress your spring by minus u, so that remember the positive sign is downward, so upwards it will be negative sign. By minus u, then the relative displacement is denoted by minus u. So it is always the relative displacement with respect to the equilibrium position. So these are two very important facts, three very important facts initially about the setup of the problem. You must remember these three facts before you continue with anything. This is going to be very, very important. Okay, so remember, we're measuring the mass with respect to the equilibrium, and we just see how much relative displacement you have with respect to equilibrium position. For example, here you displaced by u. Here you again you displaced by u. But these two u are different because one of them is downwards, so that will be positive, and that one, and the other one is upwards. It will be negative. Is that good, family? Okay, so that's kind of how we describe this motion. Okay, so now once you know that the position of the mass is described by the u, then you can see that starting from the initial time, the motion, okay, so the motion of this mass, okay, so with respect to time, can be described as a function u of t, where u is actually the relative displacement with respect to the initial, right? So initial, so equilibrium position. So that, for example, here, initially, you already have a positive u. And then you start to oscillate, so at different times, the u of t is going to be different, right? So it describes the oscillation by a function u of t. So that's the goal, okay? So the u of t is what we want to model. So differential equation, so let's say ODE for u of t, I just want to find this object. You want to find a differential equation that describes the relative displacement with respect to the equilibrium position in terms of time. Is that good, family? Right? So you want to describe this. So this is the final goal, right? So you want to describe this u of t. Now, how do we describe formulate the differential equation that can describe u of t? Right? So that's kind of going to be an interesting problem, right? So how do we do that? Well, we're going to do so-called analysis of forces, right? So this is what you learn in your physics classes. So that means the original spring has a length L, and then initially you have elongated this one by capital L. This is going to reach an equilibrium position. Is that good, family? So that means mg is equal to kl, where k is the Hooke's constant. Is that good, family? Now, what happens if you have a u of t? So let's say assume, okay, so we're going to assume u is positive. I mean, if u is negative, then everything is going to be, everything is going to reverse its sign, and it will not affect the result. So that's the good advantage of taking a signed position. Okay, so signed displacement, but it's completely fine. Okay, so let's say L plus L. Okay, so let's say initial displacement is with respect to another u. So that means let's say this is the L. This is L, you're going to replace by another U. So now we are going to analyze the forces. How many forces are acting on a mass? Okay, so by Newton's second law of classical mechanics, we know that the forces, okay, so the forces acted on a certain mass is always equal to the mass multiplied by the acceleration. So that's the Newton's law of acceleration. Is that good, family? But what is acceleration? Well, the acceleration is simply d squared u over dt squared. It's a second derivative of the position. But here the position can actually be described by the relative displacement. So that means you just have to take a second derivative of the relative displacement. That's going to give you the acceleration. Is that good, family? So the goal is now to just analyze the force, right? To analyze how much force is being acted on the mass. So how do we analyze the force? Well, initially there should be mg, which is just the gravitational force acting on a mass because you're in a gravitational field. Is a good factor mg. Now, but there's going to be resistance, right? So how much resistance do we have? Well, the resistance is going to be kind of given by k multiplied by u plus l. Because here you have deformed, right? So you have deformed your spring by a distance L, then additionally by U. We're going to assume U is positive. So that means the resistance force is KU plus L. But remember, we're going to take the positive direction as downwards. So therefore, anything upwards is, in terms of sign, is a negative sign. Is that good, family? Okay, so that means you're going to kind of have a resistance force that's equal to KU plus minus KU plus L. Is that good, family? Okay, so that's going to be the ideal scenario. Now, we're going to consider a real-world scenario that means the whole system, right? So the whole system, that means the mass and the spring, somehow are immersed in a certain media. It's not in a vacuum, okay? It's not in a vacuum, but in a certain media. So in a certain media, it's going to usually it's going to exert the media, okay? So the environment is going to exert a certain damping force, okay? So that's we're going to call it the damping force. So the damping force is usually caused by friction, right? So let's say, imagine that your system is immersed in oil. Then it's not going to oscillate much because there's going to be a lot of friction, right? So that oil exerts on the mass. So this friction force is actually turning the kinetic energy into heat. Or in other words, we say the friction force is producing entropy. Is a good favorite, right? So that's what you learn in your thermodynamics class, that you're going to always, okay, so you're going to always create a certain heat from kinetic energy due to molecular collisions in the friction. Is a good favorite. Okay, so that's kind of, it's an entropy production process. Is a good favorite. So the damping force is also sometimes also called the friction force. Okay, so sometimes also called the friction force. It's given by minus of gamma multiplied by u, where gamma is the so-called damping constant. Okay, so gamma is sometimes called the damping constant. Okay, so the damping constant. So with the damping constant at hand, you can see that the damping force is just a negative of the damping constant multiplied by displacement, which is kind of reasonable, right? So, not displacement. Here, the damping force is usually given by minus of the damping force multiplied by the first derivative of the displacement. Is a good fabric. What is the first derivative of the displacement? The first derivative of the displacement is the velocity. So that's kind of reasonable because it says that the damping is always opposite to where you move. Right? If your velocity is pointing in certain direction, so let's say if your velocity is pointing in the du over dt direction, right? So let's say v is equal to du over dt, you're moving upwards, then the damping must go downwards, gamma of v. Right? Because the friction is always kind of trying to prevent you from your current motion. Is that good, family? So that's going to be negative of the gamma multiplied by the velocity. So there's going to be a damping force, okay? So here, for example, you are moving upwards, then the damping force is downwards, but you're going to be exerted by a certain damping force to the system. Is that good, family? Okay? So if you have everything at hand as this, then by the Newton's law of second derivative of acceleration, the total force F is going to be equal to mg minus the k of u plus L, as we just analyzed. And maybe it's subject to another damping force, du over dt. And this is going to be equal to mass multiplied by the acceleration. So d square u over dt squared acceleration. Is a good family. Okay, so we're going to now really reach a certain differential equation, but we have to be careful because the mg is actually kl. So that actually means that this is mg minus the ku minus the kl minus the gamma of du by dt is equal to m of d square u over dt squared. So in the end, we're going to reach a certain differential equation. It says that m or multiplied by d square u over dt squared. Okay, so but mg is a kl, so they're going to cancel. So that means this thing plus gamma of du over dt plus k of u is equal to 0. Is that good, family? Okay, so this is a second order differential equation. This is a second order differential equation that can describe this motion without any external force. So what I'm saying is that why I say external force, that it means that you're acting to the mass externally. For example, you manually push it or you manually drag it. So without doing anything like this, if you let the mass move freely in the atmosphere in a certain environment, then you always have this exerting on this mass. There's going to be gravitational force due to the gravitation, and there's going to be resistance by minus k of the u plus L, and there's going to be damping due to the environment. You're not exerting any other manual force onto it. Is that good, family? In that case, the motion is described by the relative displacement, as we explained, and the relative displacement simply satisfies this very simple differential equation. Is that good, family? Okay, so if you look at this differential equation, okay, so if you look at this differential equation, what do we have obtained in the end? Well, we just have obtained in the end, okay, so we just have obtained in the end a certain simple, very simple differential equation that's just given by this. Is a good family, right? So that's just going to be given by this. And this differential equation is nothing, okay? So it's nothing but mu double dot plus gamma of u dot plus k of u is equal to 0. This is a type of differential equation we really know how to solve. Is a good family. What's this type of differential equation? It's a homogeneous, okay? So it's a homogeneous, okay? So constant coefficient ODE. Second order ODE. It's a homogeneous constant coefficient second order differential equation. Very simple, homogeneous. And this we know how to solve it. We know we solve it by characteristic equation. So this is a good application of what we have learned so far regarding the characteristic equation and characteristic rules and fundamental solutions, the Wronskians, linear combinations, real complex, real repeated roots, real distinct roots, complex roots. We're talking about everything about how to solve a homogeneous constant coefficient, second order ODEs. And this is just an application. We just need to solve it. And then once we solve it, so then the exciting thing here is that as long as we have solved it for this u, we obtained a relation. Okay, so we obtained a relation of, we obtained a relation in terms of time regarding the motion u. So we can really have this curve, how it's look like, because we know how the u is going to look like. Is that good, family? So that's a homogeneous case. That's a homogeneous case. Now, we've been talking about external forces, right? So what does it mean, external forcing? Well, external forcing simply means that you're going to drag this particle by external forcing. So the external forcing is a function of t. Is that good, family? At different times, you're going to give different external forces to the mass. Is that good, family? Okay, so that's going to be a second, external forcing. So once you have the external forcing, you see that the left-hand side of this equation can be replaced by F is equal to the external forcing of T. Okay, so plus mg minus k of u plus L minus gamma of u prime. That's going to be equal to m of u double prime. I replaced the derivative by u prime and u double prime. So that's the same thing. You're going to see that this is the external forcing. Okay, so mg kl is going to cancel as before. So that's minus ku minus gamma u prime is equal to mu double prime. So in the end, you reach another differential equation that's going to give you, okay, so you reach another differential equation that's going to give you mu double prime, okay, so plus gamma of u prime plus k of u is equal to the external forcing. This is the non-homogeneous version of your differential equation. Is that good, family? Okay, so the non-homogeneous term on the right-hand side, if you put it on the right-hand side, it's just equal to the external forcing. Is that good, family? Okay, so this is going to be your non-homogeneous version of the motion of this vibration. Is that good, family? Okay, so that's the non-homogeneous version of the motion of the vibration. Is that good, family? Okay, so let's put this equation maybe here. Okay, so that's the non-homogeneous version of your motion in the vibration. So that's kind of, this is going to be the non-homogeneous version of your mechanical vibration. So non-homogeneous. Okay, so constant coefficient, right? So second order, okay, so second order ODE. So we reached both types of ordinary differential equations that we have been interested in our previous lectures, right? So very important thing for the previous lectures is that we just were talking about how to solve these type of equations. But now you see real concrete applications because we know, as long as we know how to solve these equations, we can solve these concrete equations from which we're going to obtain, okay? So from which we are going to obtain a certain kind of U that describes the real motion of this mass. Is a good family? Okay, so that's going to be very, very important. Is a good family? Okay, so that's kind of a very good remark. Okay, very good remark. Let me make a few remarks. Okay, so the few remarks is regarding this. Okay, so if you look through this modeling process, the important thing that you must understand that this U is the relative displacement with respect to the equilibrium position, where the downward direction is always going to be positive. So that's going to be very important. Is a good family? Okay, so that's one thing, is that you must understand what this U is, The second thing is that you must remember these coefficients, right? So the first coefficient, second coefficient, and third coefficient, each coefficient is going to have a concrete physical meaning. Is a good family? Now, if you want to memorize these coefficients, it's very simple. Just to realize that in front of the second derivative, it is the mass. In front of the first derivative, it is the damping constant. In front of the zeroth derivative, the original function, it is a Hooke's constant. So don't mess up, okay? So must remember, in front of the second derivative is the mass. In front of the first derivative is the damping constant. In front of the zeroth derivative is the Hooke's constant. Is that good, family? Okay, so this is going to be very important. You must memorize it by heart. Okay, you must memorize it by heart. Now, as long as you have, we have both of these remarks, we now have a nice model. Okay, so we now have a nice model for my differential equation, right? So that's it's going to be mu double dot plus, remember, damping constant in front of the first derivative, Hooke's constant in front of the zeroth derivative, external forcing is going to be on the right. So that's going to be a differential equation that describes the relative displacement U as a function of t. But this is not enough. Why? Because this, as we learned in our previous lectures, if you give me such a differential equation, then when you solve it, you're going to reach a so-called general solution. The general solution are going to have some constants that's not going to be determined. So you're really not going to reach a certain particular solution if you don't prescribe initial conditions. Is that good, family? According to what we have learned previously, the initial conditions should contain the initial position. U0 is U0, and the initial velocity. Remember, U prime is the velocity. So that's the V0 is the initial velocity. And once you have the initial conditions, from the initial conditions, in terms of a set of fundamental solutions, you're going to be able to find those constants and finally reach a particular solution. Is that good, family? Okay, so that's going to be very important. But what does these initial conditions mean physically? Well, physically, its situation is pretty simple. So the initial conditions simply, for example, here, if you drag this mass, elongate the spring a little bit different by U, then it means that the initial position is U. And this is very important. If you don't know where you start, you cannot describe the oscillation. But however, if you just drag this mass by a distance U and release it, then the initial velocity is going to be 0. So that's like you release it freely. Is that good, family? But there might happen that when you release it, you give additional kick. So there's going to be additional velocity. Initially, it was moving at a certain speed. Then the speed is going to affect the motion also. So the initial position and the initial velocity, they have quite concrete physical meanings. If you think about the physics, it just means where you start and at what velocity you start. Is that good, family? As long as you have all this information, you should be able to solve this differential equation by what we have learned in our class. Is that good, family? Okay, so that's the goal. So, and it also shows the predictive, okay, so I would say it also shows the predictive power of differential equation. Why we learn differential equations? Okay, so why do we want to spend time on differential equation? It is because we want to make use of the predictive power of differential equation. So that means the differential equation can predict future, right? So this is, prediction of future is something that people are looking for throughout our civilization. Throughout our civilization, the major thing is that we want to know, we don't know the future, but we want to find a certain way to know the future. And this is civilization, right? So for example, people are talking about machine learning, right? So data science. All this is means that you have the data, you want to predict the future. And differential equation is actually in this way.
So it means that if you have the parameters of the system, right? So you have this mass, you have the damping constant, you have the Hooke's constant, initial velocity, then I can deterministically predict the future by solving the differential equation. So this is why it is very important, especially for engineering. Any practical problem in the world is about predicting the future. Is a good family, right? So that's, we want to have controls over the future. Is a good family. Okay, so that's going to be the situation on the differential equations. Okay, so here I would like to show you some examples. What kind of problems you're going to encounter on your exams? Okay, what kind of problems you're going to encounter on your exam? So on the exams, the problem is going to say that something like this. Okay, so description. So look at this problem. It says that you have a mass, its weight in 4 pounds, stretches the spring 2 inches. Okay, the mass is displaced additional 6 inches in the positive direction, then released. Mass is in a medium that exerts a viscous resistance 6 pounds when the mass has velocity 3 feet per second. Can you formulate the initial problem that governs the motion of the mass? Okay, so the important thing from this type of problem is that you want to write a differential equation like this. So you will need m, gamma, and k to determine them, and external forcing as u0, v0. All these unknown factors are something that you have to read from the text of the problem. M, gamma, k, the external forcing, u0, and v0. So there are 6 parameters that you would like to determine. Is that good for everybody? Okay, so for example, for this problem, the weight is 4 pounds, but the weight is not the mass. In terms of pounds, the mass weight coefficient, this is Newton's gravitational coefficient, is 32. So that means you have to do 4 divided by 32. That's the mass is 1/8. So that's the mass. How do we read the Hooke's constant? Well, remember, the Hooke's constant is saying that initially, okay, so initially the stretch of the spring is 2 inches. So that, remember, mg is equal to kl, right? So mg is the weight. So weight is 4. Kl, 2 inches, but you have to, you see, the very important thing for this type of problem is that you have to use a unified measurement of your units, measurement of units. Because here's the feet and inches. You know that 1 feet is equal to 12 inches, right? So that means in terms of feet, 2 inches is 1/6 feet. So that's the distance, which is the L, right? So KL is mg. So that's K is equal to 4/1/6. Is that good for everybody? Okay, so if you're not kind of very confident about yourself, you can write something, right? So let's say mg is equal to 4, because the 4 is what is written here. And you know that g is equal to 32. So that is going to tell you that m is equal to 4/32, which is 1/8. And secondly, you're going to know that mg is equal to kl. And you know the Hooke's constant k, right? So you want to calculate Hooke's constant k. So the k is mg over l. It's going to be 4 over the initial displacement is 2 inches. So that's 2 inches. You're going to use 2/12. That's going to be the feet. So that's 4/1/6 is going to be 24. You can just do some scratch work. Is a good favorite. You can do some scratch work, right? So as it was shown here. So what about the damping constant? Well, the damping constant says that the medium exerts a viscous resistance of 6 pounds with a velocity 3, right? So that means the 6 pounds is going to be with velocity 3, so the gamma multiplied by 3. So that's going to give you, okay, so that's going to give you gamma. Okay, so gamma is equal to 6/3 is 2. So you have everything, right? So as long as you have everything, you must remember the mass is with respect to u double prime, and then the gamma is going to be with respect to u prime, and the k is going to be replaced by u. What about external forcing? Is there any external forcing in the problem? Well, you didn't see it, right? So it says that you're just going to release it. Therefore, the external forcing is 0, and that's going to give you the differential equation you're looking for. Is that good for everybody? But this is not enough, because you must give me, okay, so it says the initial value problem. So you must give me the initial values, which means the initial position. What's the initial position? Additional 6 inches in the positive direction. That means downwards. Is that good for everybody? Okay, so that means u of 0 is additional 6 inches is 6/12. It's kind of going to be 1/2 feet. And what about the u prime of 0? What's the initial velocity? Well, the initial velocity says that you then release it. Release it means release it freely. You're not going to have initial velocity. That's going to be 0. So the whole thing is kind of described by such a system of such an ordinary differential equation with initial conditions. And this is the typical type of problem that you're going to see on an exam. Okay, so this is the typical type of problem you're going to see on an exam. Okay, so let's look at another example and practice what we have learned here. Okay, so here it says that you have a spring. It hangs vertically from the rigid support. When a 2-pound box is attached to the end of the spring, the box stretches the spring 0.5 feet and then comes to rest. Okay, so suppose the object is lifted up 2 feet from the rest position. Okay, and then released. Assuming the air resistance or the damping force at any instant is equal to half the instantaneous velocity in the box, can you write but do not solve an initial value problem that models the motion of the box? So that's kind of, again, a vibration problem. So you want to kind of read the data, right? So you read the data. So how do you determine the mass? Well, it says that the 2-pound box is going to stretch the spring by 0.5 feet. So that's going to be saying that mg is equal to 2 pounds. So the g is equal to 32, remember, in terms of pounds. So m is equal to 2 over 32, which is just 1 over 16. So that's the mass. Is that good, family? Now, what's the second thing? Well, you have the box is stretched in the spring 0.5 feet. So that means and comes to rest. So mg is equal to kl. So you can see that k is equal to mg, right? So mg is equal to 2 divided by l is 0.5 feet, right? So that's you're going to see 0.5 feet. And in terms of 0.5 feet, so that's 2 over 0.5, k is just equal to 4. Is that good, family? Now, what about the gamma, damping constant? Well, the air resistance or the damping force is kind of clear. It's equal to half the instantaneous velocity. So that means the damping constant is just 1/2. It's half the instantaneous velocity. Is that good, family? External forcing is 0. So therefore, you're going to have a differential equation. It's 1 over 16 multiplied by the mass multiplied by u double derivative plus the k, the gamma is 1/2 of u derivative plus k is equal to 4. So that's going to be a 4, right? So 4. Okay, so maybe I will clear this. Okay, so that's 4 times of the u is 0. So that's going to be your differential equation. Okay, so that's going to be your differential equation. But this is not enough. You have to know the initial position. What is the initial position? Initial position says that initially you're going to lift up 2 feet from the rest position. This is very important. If I say lift up 2 feet from the original length of the spray, there's another story. Is that good, family? Okay, so you can think about it. But what about the lifting just from the rest position? It means you deviate from the rest position is the equilibrium position by 2, but this is up. So therefore, if it is up, you must be -2 because the downward direction is positive. And what about the initial velocity? Well, initial velocity is that then comes to, then released. You're not going to give it any initial velocity. The initial velocity is 0. So that's going to give you another differential equation. That's what you're looking for. Is that good, family? So these 2 examples are nice examples showing that how you're going to solve such problems on exams. Okay, so I can guarantee you, okay, this is for sure. This is for sure that the next exam is going to include such problems. There's no possibility to avoid them. Okay, so you will see such problems in your next exam. Is that good, family? Okay, so that's kind of, please get yourself prepared. Okay, get yourself prepared. So now we can come back. Okay, so we can come back. We still have some time. Okay, so now we can come back to our mechanical vibrations. Now we know that the whole thing is kind of described. Mu double dot plus k. Okay, so plus gamma. Okay, so plus gamma of u dot plus k of u is equal to the external forces in terms of t, and u of 0 is equal to u0 and v of 0. Okay, so u prime of 0 is equal to v0. So that's going to be your differential equation. Is that good, family? Now we want to see how much predictive power can we have on this differential equation to describe the actual vibration, right? So you said that it has a predictive power. So that means we can definitely talk about this vibration and see how it predicts, right? How much it can predict you from these knowing conditions. Is that good, family? All right, so how do we do the prediction? Well, we want to solve the differential equation. Here I will solve this differential equation by several situations. Here I will first talk about so-called undamped free vibration. Okay, so by undamped free vibration, it means there is no damping and there is no external force. So damping is 0 and external force is also 0. So the undamped free vibration is just differential equation mu double dot plus ku is 0. So what does it mean? It means that you're exerting your experiment system in vacuum. There is no damping. And it's a free vibration. It means that you are not going to have any external forcing on the mass. So you have just a very simple equation. And how do you solve it? Well, you solve it by characteristic mr squared plus k is equal to 0. You know that r1 and 2 are equal to what? Is equal to the square root of minus k over m. But if you have this, it means that it is I times k over m with a plus minus sign. They're imaginary, right? The common in pure real part, the common real part is actually equal to what? Is 0. And common complex part is what is given here. So that means the solution u of t is equal to c1 e to the power of what? The exponential. Real part enters the exponential, there's no real part. And complex part enters sine and cosine. So sine enters cosine square root of k over m multiplied by t, and then plus c2 of sine square root of k over m multiplied by t. That's going to be your oscillation. Is that good, family? Okay, so that's going to be a very, very simple situation that you have undamped free vibration. The general solution is going to give you such form. Is that good, family? Okay, so in general, it can be written. Okay, so it can be written as if you set omega 0 is equal to square root of k over m, then you're going to see that u of t is equal to a cosinuses omega 0 of t plus b of sinuses of omega 0 of t. So that's going to be the situation. Well, this omega 0 has a very, very important, okay, so is a very, very important quantity in our later applications. Is that good, family? Okay, it is going to be called the natural frequency. It is going to be called natural frequency. Why it is called a frequency? Well, it is called a frequency because the motion itself in this form can actually be written as just an oscillation. So why? Because you can see that, okay, so you can see that this one can actually be written as the square root of a squared plus b squared multiplied by a over the square root of a squared plus b squared multiplied by cosinuses of omega 0 of t and plus b over the square root of a squared plus b squared multiplied by sinuses of omega 0 of t. Is that good, family? As long as you have this, I will claim that this is r multiplied by cosinuses of omega 0 of t minus, okay, so minus a certain phase, let's say delta, where it satisfies the following scenario that the tangent delta is b over a. Okay, so the r is equal to the square root of a squared plus b squared, and the tangent delta is equal to b over a. This is kind of a very elementary trigonometry. Is that good, family? Okay, so just remember that if you want this form, so let's say I'm giving you a hint. Okay, so the hint is that r, okay, so cosinuses of omega t minus the delta is actually equal to r of cosinuses of omega 0 of t. Okay, so cosinuses of delta plus sinuses of omega 0 t, right? So multiplied by sinuses of delta. And that means you just want cosinuses of delta is equal to a over the square root of a squared plus b squared, as well as the sinuses of delta is b over the square root of a squared plus b squared, which is just given by this tangent delta. Is that good, family? Okay, so as long as you describe the u in this form, you can see that the motion, okay, so the motion as we have seen in this picture, okay, so the motion as we have seen in this picture is just given by a trigonometric function. By a trigonometric function, it means that the trigonometric function is just the cosinus function. So that means the motion is just given by a motion by cosine. So this is actually the trajectory. Okay, so let's say in terms of u, this is actually the trajectory of a standard, okay, of a standard vibration problem, which we call it undamped free vibration. If you consider the undamped free vibration, you're going to have a motion like this. And if the motion is like this, according to trigonometry, the omega 0 is actually the frequency. It's the frequency of this motion where the corresponding period is equal to 2 pi over the frequency. Is that good, family? Right? The corresponding period is going to be 2 pi over the frequency. And therefore, this frequency is going to be called the natural frequency. So that's going to be very, very important quantity in our later discussions. It's going to be called the natural frequency. Okay, so I'll stop here. Okay, so that's what I want to say for today's lecture. Let's stop here, and we're going to come back to vibrations in our next lecture. Okay, so see you in the next lecture.